Okay, let's see how bond enthalpies could be used in an example question. So the combustion of methane is shown below in the balanced chemical equation. The first step to using bond enthalpies is to figure out what bonds you have, to figure out what bonds are being broken and what bonds are being formed. So you have to draw out the structures of all the reactants and all the products. Now that's CH4, that's methane, O2. Now I'm going to draw it twice because it's shown twice. So this is saying one methane reacts with two O2 molecules. Then I'm going to make a carbon dioxide molecule. And I'm going to make two water molecules. Notice that because I'm focused on the bonds, I'm not drawing in lone pairs. But that would be something you'd do if you were drawing a proper Lewis structure for a different kind of question. Now, the nice thing is that our unit focuses on fossil fuels and combustion. And so most of these structures you're going to see again and again and again. You're going to see O2 in every combustion reaction. You're going to see carbon dioxide, and you're going to see water in all of our examples of combustion. So once you practice those structures, they should be pretty quick to draw. You won't have to really put a lot of thought into it before you sketch out the structures with the bonds. Okay, so we've drawn all of those structures. And now we have to find the bond enthalpies. So I can see that in the reactants, I've got C to H bonds, and I've got O to O double bonds. And I've got 4 C to H bonds, and I've got 2 O to O bonds. Then on the right-hand side, I've got C to O double bonds, and I've got O to H bonds. I've got 2 C to O bonds in total. There's 2 in that carbon dioxide. And I have 4 O to H bonds total. All right, so now I would go back to the data table and find them. So let's see, I've got CH is 414. And I've got C to O double. We found that before. That was 804. Ooh, that goes over here. I've got the O to O double, which is 498. Let's erase that first. Nope. And then I've got O to H, which I'll find here, and that's 463. Okay, so these are the actual values for each bond. And then if we're going to calculate all the bonds needed to be broken, I need to break 4 C to H bonds. Right? If I think about it, if I color it in, I have to break all 4 of these bonds. And I have to break both of these O to O double bonds. So basically I just have to add up all of the bonds in the reactants. Okay, so 4 times 414 plus 2 times 498. And obviously you can use a calculator. I'm going to do that right now. 4 times 414 is 1656, and 2 times 498 is 996. And so if I add those together, I get that I have to put in 2,652 kilojoules, kJ, to break all of the reactant bonds. Okay, now I'm going to repeat that process for the products. This is the energy that I'm going to get out when these bonds form. So it's going to be 2 times 804, those are the C to O double bonds, and then it's going to be 4 times 463. Once again, let's use our calculator. That's 1852. And if I add that and 1608, I get 3460 kilojoules. Okay, so let's pause for a second. The first value in part C, 2,652, this is the energy required to break the bonds. This value is an energy amount that has to be put in, that has to be absorbed in order for these bonds to break. Now I'm going to start to do part E as I discuss. We're going to add arrows to show bonds breaking and bonds forming. So bond breaking is always endothermic. And endothermic changes are positive. Energy goes in. So if I start with the reactants, I have to put in 2,652 kilojoules to break apart the reactants and get a bunch of separated atoms. Okay, Then when I form the bonds, I get out, so this next value is energy out. 3,460 kilojoules out. When energy goes out, that's exothermic. And we think of that as a negative change. The system is losing energy. Also, if we think about it just in terms of how big I'm going to draw these arrows, if this arrow up represents 2,652 kilojoules, then my arrow pointing down right now is going to have to be bigger than that, because 3,460 is a bigger number than 2,652. So I can see, whether I look at the graph on the right, the energy diagram, or the answers in C and D, the amount of energy I'm getting out is bigger than the amount of energy that I'm putting in to break the bonds. And that means overall, the change here is going to give me some energy out. So down here, these were our products. And this difference right here between the reactants and the products, that's the delta H value. And the delta H value is just the difference between where you started and where you ended. And so for us, it's also going to be equal to the difference between the energy in to break the bonds and the energy that you get out to form the bonds. So you put 2,652 kilojoules in, and then we get out, and this is why I'm going to use a minus sign here. We get out 3,460. So 3,460. And so the difference is minus 808. So that is the energy change when this reaction takes place.